exponents and logarithms, right? The exponent function is basically means powers. All right, so for example, if you have y equals a number, so that's called the base number, all right, to a power that is variable. So in other words, you're used to seeing polynomials, for example, y equals x squared or x cubed, etc., etc. All right, but this time it's a fixed number that's raised to a variable power. All right, so y equals whatever a is to the power 1, to the power 2, to the power 3, etc. All right, and effectively what that means is that the graph, okay, if I do a little sketch of that, let's start. If a, for example, is 2, all right, then when x equals 0, right, y equals 2 to the power 0. What's that?
1.
Absolutely. So it's going to go through y equals 1, right, on the y-axis there. So that's 1. Okay. The next one, 2 to the power 1 is obviously 2. The next one, 2 to the power 2, is going to be 4, etc. All right. So schematically, we know that it's going to get steeper and steeper and steeper as you go along, like that. Now, on the negative side, you will have, for example, y equals, at a particular point, if I had 2, and you go minus 1, all right? What does that actually equal?
A half.
Yes, it is, exactly. What's going to be the next point?
Minus 2 for a second.
Yeah, right. Yeah, fair enough. Go back and watch my indices video, all right? So a half. And then the next one, y to the minus 2. So, sorry, 2 to the minus 2 is going to be a quarter. It does not become negative, all right? So that line is going to carry on. It's going to approach 0, but never actually get there, all right? And the exponent function, the exponential function, if a is positive, all right, it can never, y can never be negative. Okay, so if a is greater than 0, y is always greater than 0. Okay, that is a rule. So in other words, that graph can never cross the x-axis. Okay, all right. Are you with me so far?
Yes.
All right. So examples of that, as we said, y equals 2 to the x, or, I mean, it can be any number you like, yeah, whatever the thing says. The other thing is that if you have a fractional a, right? So now picture it as a is between, all right? How should I write this? Between 0 and 1. So a is fractional. For example, y equals half to the power x. All right? Y equals half to the power x. Right? Now what happens here? If you have a negative power, so half to the power minus 1.
Okay.
Exactly. Right?
So
It's the opposite way around. Okay? So if I were to draw that on the same thing, let me just get my color up there. Okay? If we had this thing, it would mirror exactly that other one, right? So it would do something like that, all right? So it flips around, okay? Fractional powers are going to go from high on the negative side and approach 0 on the positive side of x, whereas the original number, i.e. an integer number 2 or 3, whatever, that's going to follow the standard one. Low, approaching 0 on the negative x and climbing to very high numbers on the positive x. Does that all make sense so far? Yeah? Okay. That literally is all there is on exponential functions and the graphs of them. Okay? In as far as your basic stuff goes on exponents, you're not going to have to deal with negative powers. Negative base numbers. So a is negative to some power. You won't have to do those. Those behave very differently, as you can imagine. All right? Because if you have a is negative, all right, then every odd power, right, is going to be a negative number, and every even power is going to be an even number. Do you get it? So the thing's going to go up and down wildly. All right? So you don't have to deal with those. You're dealing with continuous functions like this. Okay? Any questions so far on this? All right. So that's the basics of exponentials. All right. Very simple. The next thing you asked for was the logarithms. All right. Okay. Let's go back here. So logs or logarithms, right? It's basically saying, so if I say, for example, 2 to the power 3 equals 8, all right? Simple rule, you know that, fine. Okay. What effectively a log says, all right, is, for example, if I were to say, what is log 2 of 8, right? And it's written like this, log 2 of 8, okay? That expression in plain English means this. What power, or, and this is where the exponent thing comes in, what power or exponent of 2, right? That's where the base is there, all right? What power or exponent of 2 equals 8. So that expression, log base 2 of 8, is this sentence. That is actually what it means in plain English. All right. So we already have that answer. I mean, in other words, if you know it, that one is 3. All right? So does that make sense?
Yeah.
Yeah? And therefore, log 2 of 8, in other words, what power of 2 equals 8? And that is 3. So 2 to the power 3 equals 8. Right? Plain English. And you can do that for anything. So if I were to give you this example, log 10, right, of 10,000. Absolutely. 4. All right? Do you see how that works now?
Yeah.
Okay? All right. Some basic rules. Okay. No, actually, I'm not going to change that. That's fine. One specific thing, note, log 10 is written simply as log, all right? So if there's no number after the log, you assume it's 10, okay? All right. Any other base, you have to write, let's say, must be shown. All right, it has to be specified. So for example, log 2, log 3, etc. So anything other than base 10, okay? Log on its own is base 10. All right, so you understand the whole log business as far as the base goes, right?
Yes.
and what a logarithm actually means. All right, so you've got all that. Then there are some things called, in other words, how to do calculations with logs. All right. Do you need any more examples on log
No.
actual working them out, right?
No.
And you know how to do it on the calculator?
Yes.
Yeah? Okay, fine. So then we have this thing called the log rules or log laws. How to combine and sort of carry out calculations with them. All right? And these are very important. You don't have to prove them or anything, but you need to know how to manipulate equations or expressions with different logs in them. All right. Okay, first one. If you have, what did I just do? 1 second. Okay. If you have log A, all right, plus log of B, all right, and the logs have to be of the same base, all right. So in this case, we're going with, obviously base 10, all right. As long as the logs are of the same base, then you can combine one log plus another log into the product of the two numbers. So log A plus log B is the same as log of A times B. Okay? Combined. Does that make sense? Yeah? All right. Then you have log A minus log B will be log of A divided by B. Okay? Combining them that way. All right? Then there's one other simple rule. If you have log A and the A is to a certain power, all right? So imagine that that's B there. Okay, so log of A to the power B, all right? You can bring the power to the front and it becomes B log A and vice versa. Let me show you an example of that. So if I have, bear with me. What did this do? There. Okay. So imagine you've got log 2, all right, of 16, all right? We know that that is what power? 2 to what power? 4,
Yeah.
right? So 4th power. What if we wrote that, right, as log 2 of 4 squared? Do you see that's exactly the same thing, isn't it? 4 squared and 16, right? And if we now brought the 2 to the front, okay, like that, so you have 2 log 2 of 4. What's log 2 of 4?
2.
Exactly. So you have the 2.
Plus 2 is 4.
Yep.
Okay.
Do you see? All right.
Yeah.
So again, you can go either way. If you have a coefficient in front of the log, you can apply it as a power to whatever is inside the log. Or if you have a power on the inside of the log, you can bring that out to the front as a coefficient. Okay? So these rules, as we've just seen, okay, these things you are expected to know and be able to manipulate equations with those.
Okay.
All right. Okay. Any questions so far on those? No? All right. Later on, we can do some questions and you can practice some questions on how to solve equations and things like that. All right.
Okay.
All right. Finally, there's one that is a bit special. It's an odd one that everybody in year 12, they sort of pick up on, but they don't know quite what it is. It's called the natural log. All right? And this is going to take a second to explain, or a few seconds actually. Let's draw. Okay. All right. We've already said that any exponential graph, right, is going to a positive base, is going to get higher and higher, like increase in value as it goes towards positive x. All right, so we know that gets steeper and steeper. But every single one, no matter what the base, is always going to cross the y-axis at 1, because any number to the power 0 will be 1. Okay, all right. Then, and if I do different colors now, so imagine that that is 2 to the x. All right. If I have 3 to the x, it's going to get steeper more quickly. All right? Because the base number is obviously bigger. All right. So 2 squared is 4, but 3 squared is 9. So it's climbing faster. All right. But on the flip side, on the negative side, it's going to approach 0 more quickly as well, because the fraction is smaller, right? Which we saw right at the beginning of the discussion. Okay, makes sense? All right? Okay. And so on. So you can see, if I were to go with, 4, for example, like that. Okay. So that could be 4 to the power x. All makes sense so far? Yeah? I'm sorry, I know it's a bit bright on the screen, but can you still make sense of what's going on? Yeah? Okay. Now, this is the important bit. In all of these numbers with the different bases, whether it's 2, 3, 4, or gazillion, right? There is a special one, okay, somewhere in that range, and I will demonstrate. Okay. Such that, obviously it goes through 1, all right? But again, it rises like that, okay? There is a very special number, a, all right? So a to the x. Now this is the important bit. Such that at x equals 0, right, y equals 1, and gradient equals 1. All right? Okay. And then what happens? It can be shown for this special value of a, such that, right, and this is really important, such that at all points on the curve, yeah, y value also equals the gradient. Actually, whoops, what did I just do? All right. So effectively what that means is, at all points, the value, the y value of that point, so the y coordinate, right, and the slope, the steepness of the slope, are always the same. And now if you put it in calculus terms, right, because you've done the basic differentiation, that effectively means that dy by dx, right, equals y for all x. Okay? That is a very special relationship. Okay? And this occurs in nature a lot, right? Radioactive decay, charge on capacitors, and all sorts of other things in nature. Okay? Populations of animals and things like that. Okay? Right. Now, having said all of that, what is this special value of A? Okay? We call it E. All right? E to the power x, effectively. All right? And that is defined as y equals e to the power x. That is the special value of A, E. All right? And if you punch it into your calculator, can you find any calculator?
Yep, I'm sure.
Down at the bottom, just press, what is it, shift or something, and press E, and tell me what the value you see is.
2.71
2.718.
8281828.
Yeah. I usually remember it roughly as 2.7183. Okay? If you were to, in your mind, just have 2.7 as a rough indicator, that just gives you a feel for what the number is. All right? So that is E. All right? And that thing is spectacularly important in maths in your later stages, all right? Whether it's in calculus, in differential equation things, rates of change, all these questions that come up in the exams, all right? This is a favorite example to use for them, okay? All right. Now, the last thing to show you, because we're onto this E thing, all right, there's a special rule. When you have y equals e to the x, all right, so that's showing you e to a certain power, all right. If you had log e of a number, right, remember I said any base other than 10, we have to actually specify, all right. So whenever you have log e, right, we don't write it as log e. That is written, and this is the one that all students sort of like have this sort of thing about mysterious fascination with, right? It's written as learn A, right? Okay, ln. It's the natural log of A. So in other words, the power of E, the exponent of E, that would result in A. Does that make sense? Yeah?
Yes.
And that's pronounced, some people say lin, and some people say learn, right? Whatever you prefer. I'm used to saying learn. Okay? Right. Any questions on any of that? On this one, right, that learn A or whatever it is, it obeys exactly the same rules, all right, as the log rules. As the log rules I showed above. Is that okay? All right. Any questions thus far? No? All right. The differentials of this, right? So differentiating, I'm not going to go into that now because I don't think you need that for your test next week, and I'll put that into a separate video if you want, all right? Differentiating logs and exponents. I'll put it in here to remind me. Separate video. Okay? Right. Any questions? Anything else on that you need for the moment? Okay?
No, but can you send me all of this after?
Absolutely. All right then. All right. Thanks for letting me do that. I'll stop there then.